Hi, today we're going to talk about radiometric dating. And this is the way that geologists are able to find the absolute age of rocks. We've already talked about how some of the different principles that geologists use to find the relative age of rocks, but today we're going to talk about absolute dating. In order to understand radiometric dating, you need to understand a few basic ideas about atoms and elements, so you need to recall what you've learned in some previous grades. So remember that we have lots of different elements in the periodic table, and each of those elements is distinct in its makeup and what particles it has, and protons, neutrons, and electrons. And so the simplest form, or the most basic form of an element is an atom. And so we have hydrogen atoms, helium atoms, and so on. Well, sometimes atoms can be radioactive, and what that means is that they're unstable, and over time they will decay. And through the decay process, they give off energy and sometimes particles as well. And sometimes they turn into totally different elements, and sometimes they just give off energy. But over time, eventually they will decay. Here's a common graph that you'll see when talking about or hearing about radioactive decay. And what this shows us is what's called a half-life. So if we take a look here, right here, the solid line here is the decay product, and the dotted line is what you start with. It's the radioactive material. So if we look in the bottom, at the x-axis we have time, and on the y-axis we have percentage. So at 0, or when the rock is born, when it will start out as igneous rock, and as soon as it starts to cool off and form a rock itself, it's going to have 100% of that unstable radioactive element. Over time, that element's going to decay. And so we see over time there is less and less and less of that radioactive element. And what happens is that turns into a more stable product. And so that's why we see the stable product, the solid line, increasing. So at the birth of the rock, there is none of the stable product because it's all radioactive. Over time, there's less and less of the radioactive atom and more of the stable atom. And we see at this point right here, when it's 50-50, when we have 50% the original radioactive element and 50% the stable decay product, that's called a half-life. And time here at the bottom, that differs for different elements. So each radioactive element that we use in radiometric dating has a different half-life. So the half-life of whatever it is we're talking about here is about 5,000 years. And after another 5,000 years, another half decade, so we can see that now we only have 25% of our original material, and we're up to 75% of our stable product. So every 5,000 years, half of this radioactive material will have changed into the stable decay product. We call this decay product daughter atoms, and the original element that we start with is the parent. So it changes from the unstable parent atom to the more stable daughter atoms. So here's kind of a visual to help you understand a little bit. So you can see here that we start with all of these red dots here, so those are our unstable radioactive atoms, and after one half-life, half of them have changed into the daughter, which is the blue. So now we only have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 and 8. 8 of our parent, 8 of our daughter. So after another half-life has passed, half of those 8 red ones will have turned into daughter atoms. So now we only have 4 parent and the rest are daughter. After another half-life, half of those 4, so 2 of them, these 2 right here, change into the daughter. So you can see the progression of the different half-lives. So one half-life means half of the remaining radioactive parent isotopes have changed into daughters. So geologists use this radioactive dating to determine the absolute ages of rock. And they're able to do this because the different elements that are radioactive and decay have set half-lives. We know what their half-lives are. So if we can figure out how much of the parent is still there and how much of the daughter is there, we can determine how much time has passed. So let's take a look right here, and I want you to try to determine how many half-lives have passed. So let's continue to use the red ones are going to be our parent atoms, and the blue ones are our daughter atoms. So take a second to figure out how many half-lives have passed, and then I'll tell you the answer. So you might want to pause it for a second. All right, so if we take a look here, we have 20 atoms altogether, and 5 of them are still parents and 15 are daughters. So if we have 20, one half-life would leave us with 10 and 10, and then after another half-life, it would leave us with 5 and 15. So we can see that we have 2 half-lives that have passed here. All right, we're going to start this example with, I've chosen over here on the right, uranium-238, which is the radioactive element that decays into lead-206. So this bucket here is how many uranium atoms we're going to start with, and let's say we start with about that many. And you can see at the bottom here, we have some things happening. So I'll show this again in a second, but the green line are the percentage of uranium atoms, and the gray line is the percentage of lead atoms over time. So let's reset this again and take a look one more time here. We'll do it kind of in slow motion. So at the very beginning, and this is, we can see the scale at the bottom here, so this is in billions of years. So we can tell that uranium has a pretty long half-life here. So this is at 0 time. So at 0, you can see we start with 100% of the uranium atoms. So it's at the birth of the rock there. But over time, that's going to start to decay. And so as we see the green line start to go down, we're going to see this gray line, the lead, come back up. So slowly, and what's nice here is we can see a visual of a pie chart over here that shows us kind of the percentage of uranium compared to lead. So we can see the uranium decreases because more and more of it is changing into the lead. And as soon as those two lines hit 50%, that's going to be a half-life, and that will tell us the half-life of uranium-238. So I think that's right about 50% there. So we can see that it's a little over, somewhere between 4 and 5 billion years is the half-life. And now after this, we're going to start to have more lead atoms than we have uranium, more of the daughter atoms. And that's just going to continue to happen over time. Now carbon-14 is another radioactive element that we use, and we use this to date things that were once living. So we're going to see a similar thing here, but you can see that the half-life is much shorter. It's much closer to 6,000 years there. And so over time, we have less and less carbon-14 and more nitrogen over here. Here's another good example to look at. This one is a little more real life for us. And so what we see here is a volcano, and it's going to erupt, and it's going to spew out some magma. And here's a nice big rock there. And once that rock has cooled, we are going to start to see, we're going to start to be able to date that rock. So on the left up here, you can see that I've chosen uranium-238 because the carbon-14 is only in things that were once living, and this rock is not living. So, and this is our little probe here. This is going to tell us how much uranium-238 there still is and how much has decayed. So we're going to start timing here, and so you can see up here that we have less and less of the uranium-238 over time. And here, this is nice because this is kind of a ticking clock that tells us how old this rock is. So if we stop it here, and this is how old the rock is, we could figure this out by looking at the percentage of uranium-238 that is present in this rock, and that percentage will tell us exactly how old this rock is. We can do the same thing with things that were once living. So here we have a tree, and if we plant the tree, let me change it to carbon-14. We're going to plant the tree, and the tree is alive now. So it has 100% carbon-14. It doesn't start to lose carbon-14 until it dies. So if we kill it now, we can tell how old it is by how much carbon-14 is remaining. So if we date the tree right now, and we see that there's 78.5% carbon-14 compared to the new daughter atoms, we can tell exactly how old that tree is. Let's learn a little bit more about carbon-14 dating. We're going to watch a little brain pop that's going to tell us about how carbon is used to date things that were once living.
What'd you find? Let me see. Oh, that's Ewan. I buried him here in the yard 2 years ago. Yeah, why don't you put him back? Dear Tim and Moby, how do scientists use carbon to date old fossils and stuff? From Strife and Beetle Docs. Scientists have lots of different ways to date fossils and artifacts. One of the most popular methods is carbon dating, or carbon-14 dating. Carbon-14 is a radioactive isotope of carbon. Isotopes are two atoms of the same element with different numbers of neutrons. The most common isotope of carbon is carbon-12 with 6 neutrons and 6 protons. Carbon-14 has 8 neutrons, and it's radioactive. It's nothing to be afraid of. Radiation occurs naturally. About 1 in every trillion carbon atoms is a radioactive carbon-14 atom. That includes the carbon inside the bodies of all living things. Carbon dating compares the amount of carbon-14 from, say, an old bone to the amount that's in a similar substance today. Well, radioactive substances are unstable. That means they decay into different substances over time. When a carbon-14 atom decays, it gains 1 proton, becoming a stable nitrogen atom. In a group of carbon-14 atoms, like the ones in your body, half of them will go through this radioactive decay every 5,700 years. If you wait another 5,700 years, half of the remaining carbon-14 atoms will have decayed, and so on. The amount of time it takes for half of a radioactive substance to decay is called its half-life. So carbon-14 has a half-life of 5,700 years. When a plant or animal is alive, the amount of carbon-14 in its system doesn't change. Well, yes, the carbon-14 in our living bodies is slowly changing into nitrogen. But we're also constantly taking in new carbon-14 atoms when we eat and breathe. Once a creature dies, though, it stops eating and breathing, so it doesn't take in any more carbon-14. From that point on, the amount in its body decreases at a steady rate, with half of it disappearing every 5,700 years. Scientists who study a life form's remains can tell when it died by comparing the amount of carbon-14 that would have been in a living creature to the amount that's left. Carbon-14 dating can only be used on the remains of living things, and it's only accurate to about 60,000 years ago. Other radioactive isotopes can measure much older things, including non-living substances like rocks. Using radioactive isotopes to date objects is called radiometric dating. Well, uranium-238 has a half-life of 4.5 billion years, so it can measure things that are as old as our planet. I don't think that's from our planet.
There are many different radioactive elements that are used in dating different substances. For rocks, we often use potassium-40 to date them, and that decays into something called argon-40, and that has a half-life of about 1.3 billion years. And so potassium-40 is very useful in finding an absolute date for ancient rocks. We also saw in the little tutorial that I showed you, and I'm going to show you another one in a minute, that we can also use uranium-238 for that. When we use radioactive dating for things that were once living, we use something called carbon-14, like you saw in the brain pop. This is something that is stable until the organism dies, and then it starts decaying. So what we can tell is how long ago the organism died. And that then the carbon-14 decays into nitrogen-14, and it has a half-life of about 5,730 years. So this is something we can use to date things that were once living within the recent past, but it's not something we can use to date, something that occurred a billion years ago, because by that time, after a billion years, there won't be any carbon-14 left at all. So here's another little tutorial to look at, and this one's a lot more real life. So we are going to use this probe to date a few different things. So let's use it to date the rock on the bottom here, and we're going to try to figure out how old it is. So first we have to choose if we want to use carbon-14 or uranium-238. So was this rock ever living? No, so we're not able to use carbon-14, so we're going to use uranium-238. So what we want to do is see right here, it shows us, right there, it shows us that this rock has 93.3% uranium-238, and the rest has decayed into the daughter atoms. So what we want to do, this is what we have up here, is the graph for all uranium-238. It tells us, based on the percentage, how old it would be. So we want to move this until we see the top showing that we have 93% uranium, which is right about there. And so that tells us that this rock is about 431 million years old. So we want to enter that in here and see if we're right. And that's pretty close. So that's about how old that rock is. Well, let's try to date something that was once living. Here we have a dinosaur skull there. So we want to change it to carbon-14. Oh, and this tells us that there's 0%. So that means that this is probably more than 50,000 years old. So let's change to this bone up here. And there is 83.9% carbon-14. So we just need to move this along the graph here and try to read it. So that's about 83.9%. So that tells us that this bone is about 1,413 years old, and that's correct. So you can see how we can use uranium-238 to date rocks, and we can use carbon-14 to date things that were once living as long as they died in the past 50,000 years. So let's go over a few important things about radiometric dating. First of all, we use it for igneous rocks, and that's because the radiometric clock begins once that rock cools. So it provides the age of when the minerals actually crystallized when the magma or lava started hardening. Sedimentary and metamorphic rocks, if we were to date them, we would be dating the individual minerals that are in them, and it would not be when the rock itself formed. We are able to date sedimentary layers by dating any igneous intrusions that might go through it or be above or below it. We've also radioactively dated some moon rocks, and the oldest ones that we can find give us a date of about 4.6 billion years old. So that gives us an idea of when the moon itself formed. That's it for radiometric dating, and hopefully this gave you a better idea of understanding the concept in the section that you read in class. And I will put a link to the Brain Pop on my big campus so that you can rewatch that if you need to.